Hello, everyone. Today we're going to look at calculating the confidence interval and doing a hypothesis test for two population proportions. So our goal for both a hypothesis test and a confidence interval is we basically are trying to figure out whether or not two population proportions are equal. So again, a proportion basically means that we're looking at either a percentage or a fraction of the population. And in this particular case, we're actually comparing two different groups. So to keep the notation simple, we will use 1 and 2 to represent population 1 and population 2. And we'll use the same notation as what we did for the first population proportion test. So we'll end up using P1, N1, X1, and P1 hat to represent stuff from the first sample or from the first population. And again, P hat is the sample proportion, and P is the population proportion. So what will be new is we're going to use what's called the pooled sample proportion. And this is where we basically take all the successes and combine them together. So we take the number of successes from both populations, add them together, and divide it by both sample sizes and add those together. So this will be like the overall number of successes divided by the overall number of data points we've collected. And of course, anytime we use Q, that just means we're looking at the complement of P. So Q bar is just 1 minus P bar. So this slide and the next slide are going to just look at some of the assumptions and formulas that we use for conducting a hypothesis test and a confidence interval comparing two population proportions. So these will use the same assumptions. So we still need two simple random samples. They need to be independent samples. And we have to have at least 5 successes and failures from each sample. So for a hypothesis test, the null hypothesis always assumes that both population proportions, P1 and P2, are equivalent. Whereas the alternative means that they are somehow different from each other. And now, if we look at our test statistic is based off the fact that we assume that the null hypothesis is true. So we're basically assuming that P1 equals P2. If we assume that P1 equals P2, then if we were to subtract them, their difference equals 0. So really, this part of the formula actually goes away. Now notice that this test statistic is actually similar to what it was in the one population proportion case. It just has a few minor differences because of the fact that we are combining two different population proportions together. Now, when we look at the confidence interval, notice that the margin of error formula is also very similar to what the case is for the one population proportion confidence interval. What you will probably notice is that anytime you compare the null hypothesis and the confidence interval, you normally get the same result. And this is mainly due to the fact that the formulas for both the test statistic and the margin of error use the same numbers. However, in this case, because the test statistic uses the pooled sample proportion, and the confidence interval in this case is actually not using the pooled sample proportion, it is possible to get different results. But in general, if you are trying to test a claim, you always want to use the hypothesis test. Otherwise, if you're trying to estimate what the difference between P1 and P2 is, we want to use a confidence interval. So in this example, we're going to basically do both the hypothesis test and on the next slide, we'll do the confidence interval for the exact same data. Now, just a warning with chapter 9 and as well as chapter 10, the formulas will actually get fairly complicated to the point where I would actually recommend doing these either by calculator or by hand. And basically, in this section, what we're going to use is for the hypothesis test, we'll end up using the 2-prop z-test. And then for the confidence interval, it's a 2-prop z-interval. And if you're using your calculator, these are located in the exact same place as the other hypothesis tests and confidence intervals. On the Excel spreadsheet, these are actually located in one sheet. So what I'm going to do is I'm going to go ahead and highlight our population 1, which is the age of 55 and over, and population 2 are those that are younger than 25. Now, I think it's pretty clear that based off our number of successes that we have here, that these are easily over 5, and we have definitely more than 5 for the number of failures in both groups. And I think it's also safe to say that these are in fact simple random samples, and that we do have independent samples. What I'm going to do is I'm going to actually first label what my population 1 and 2 are. And I'm doing this because this will make it far easier towards the end when we actually write our interpretation. So our first group, or one I'm going to label it as population 1, will be those that are over 55. And for our second population, those will be the group that are under age 25. So for a null hypothesis, we're going to assume that P1 equals P2. That's going to be true for all of these. So for the alternative hypothesis, we need to go back and look at the claim. The claim says that we assume the people over age 55 is going to be greater than the proportion of those under 25. So to write the alternative hypothesis, we need to go back and look at the claim. The claim is saying that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. So we assume that since P1 represents proportion of those over 55 is greater than those that are under 25. So P1 is greater than P2. Next step is to write the significance level, which in this case is 0.01. So for this, I'm going to just go ahead and do this all on Excel. And when I do this on Excel, I'm going to get both the test statistic as well as the p-value. So what I did was I typed in 68 for x1, 308 for n1, 13 for x2, 298 for n2, and then of course I selected the alternative hypothesis, which is that p1 is greater than p2. And I have the following output. I have both the test statistic z and my p-value, and then we have a bunch of other stuff down here. Now, another notation for the pooled proportion is p hat. So here it gives us the sample proportions, it gives us the pooled proportion, and of course it just spits out the sample sizes for n1 and n2 again. And this will be the same output that you'll see on your calculator, except I believe in your calculator they use p hat instead of p bar. Now, one thing I have to be careful of is the p-value is always a probability. It's the probability of having a test statistic as unlikely as 6.41, or in this case, larger than 6.41. Since it's a probability, it's always got to be between 0 and 1. Now you have to be really careful because our p-value actually has e-11, which basically means it's scientific notation where we take that decimal place and move it to the left 11 places. So this is a number very, very close to 0. If I was to round this to 4 decimal places, it would actually end up being 0. If we were to look at the critical value, this is a right tail test. So if we were to draw the critical region, we're only looking at that right tail. And the right tail in this case has the area of alpha, which is 0.01. So what z-score gives us an area of 0.01 to the right of it? Well, it's the same z-score that gives us the area of 0.99 to the left of it. Closest one being 0.9901, and that gives us the z-score of 2.33. Our critical value is less than our test statistic, or in other words, our test statistic is so far on the right tail that it is most certainly inside the critical region. So we end up with the exact same conclusion, both with the p-value and the critical value approach, which should always happen. Now I have to apologize for running out of room here, but the conclusion that we'd want to say is we have sufficient evidence to support the claim that the proportion of people over 55 who dream in black and white is greater than the proportion of those under 25. So in this example, this is kind of a poorly worded example. And the reason I say it's poorly worded is because it's saying we want to test the claim by using a confidence interval. What it's really trying to say is using the same data, we want to try and see if we get similar results with a confidence interval. And I have to kind of emphasize that this may be a little bit misleading that it says that this is a 0.01 significance level. Now, this is not actually the same significance level that we're going to use for a confidence interval. Both the confidence interval and the hypothesis test should always use the same critical value. The reason they should use the same critical value is so that we get this similar result. Again, the critical value is supposed to be the number that separates the values that we reject from those that we don't. And this is basically true for the confidence interval. It's to kind of separate the values that we expect to have happen from the proportions that we would not expect to have happen. From that last problem, we already know our critical value was 2.33, and that happened when the area inside this right tail is 0.01. However, a confidence interval has two tails, so this left tail must be 0.01. If that's the case, then what is the area in the middle? Well, it's basically whatever is left over, so that must be 0.98. So what we're actually needing to do is we need to create a 98% confidence interval. So again, I'm going to go ahead and use Excel, or if you have a calculator, you can use that instead. But I'm going to use the 2prop_z interval part of Excel. And my confidence interval in this case happens to be 11.57% and 23.86%. We are 98% confident the true difference between a proportion of people over 55 who dream in black and white and the proportion of those under 25, that difference is between 11.57% and 23.86%. So does this suggest that we have a similar result compared with the hypothesis test? Whether or not it does match our results. Notice that both of these numbers are in fact positive. So this suggests that P1 minus P2 is in fact greater than 0%. If we were to add P2 on both sides, notice that we would end up with P1 is greater than P2. And this basically confirms that we have the same assumption as the claim, which we had sufficient evidence to support. In this example, we're going to look at the survival rates for in-hospital patients who suffered cardiac arrest, whether they had the cardiac arrest during the day or if they had it at night. So in the day, we had about 58,000 patients, and over 11,000 of them ended up surviving and were discharged. In the second case, we had about 28,000 patients who suffered cardiac arrest at night, and over 4,000 of them survived and were discharged. So we're going to use a 0.05 significance level to test the claim that the survival rates are the same for both day and night. Notice that in this case, the claim is that they are the same. So this is actually the null hypothesis. Our null hypothesis is saying that P1 equals P2. Now I should probably specify what P1 and P2 are, or in fact just what 1 and 2 represent. So I'm going to assume that 1 represents the survival rate for those that had a cardiac arrest in the day, and 2 is going to represent those that had it at night. The alternative, well, we have to be careful because this null hypothesis was the claim, that they're equal. So the only other thing that we can say about the alternative is that somehow they are in fact different. So P1 does not equal P2. We're going to use a significance level of 0.05. And from there, we're going to go ahead and use Excel again to get both the test statistic and the p-value. Typing the values into our 2prop_z interval and test page, notice that I just typed in the x1, n1, x2, n2, and for the alternative hypothesis, I selected not equal to p2. Our test statistic ends up being 18.26, so on. Our p-value ends up just being 0. I think it's pretty safe to say that this is pretty strong evidence to conclude that we can reject the null hypothesis. For a critical value approach, remember that this is a two-tailed test, so we need two different critical values. And the area of both tails combined is 0.05, so each tail must be half of that, so it's 0.025. So from there we can get the critical value using the table or the inverse norm. So using the standard normal table, I get the negative critical value of negative 1.96, so the other one must be positive 1.96. Now if I was to draw out the curve all the way to the test statistic, our test statistic would fall very much on the far right side of our tail. And I think it's safe to say that this is definitely inside the critical region. So same conclusion, we'll reject the null hypothesis in favor of the alternative. So we have sufficient evidence to reject the claim that survival rates are the same for patients who suffered cardiac arrest at day compared to those who suffered cardiac arrest at night. Now, what's not clear is how are they different? Is it those that had the cardiac arrest at night that had a higher chance of survival rate, or is it those at day? We'll come back to this question in the next slide where we look at the confidence interval. Speaking of the confidence interval, notice that we're going to use the same critical values. So we'll end up using negative 1.96 and positive 1.96 here. So because a confidence interval is similar to a two-tailed test in the sense that it has two tails, we're going to basically say that the area of both tails combined is alpha. So each one separately is 0.025. This means that we'll actually have the exact same critical values. So our z crit is in fact 1.96. This confirms that we are going to use a 95% confidence interval. So our confidence interval is going to be 4.58% and 5.63%. Notice that in this case, both numbers happen to be positive. So this tells me that, again, if I was to set p1 minus p2 to be between these numbers, that this would suggest that p1 minus p2 is again positive. This suggests that p1 is greater than p2, or the survival rate of those who had a cardiac arrest in the day had a higher success or a higher survival rate than those who had a cardiac arrest at night. So we are 95% confident the true difference between survival rates of patients who suffered a cardiac arrest in the day versus those who suffered a cardiac arrest at night is between 4.58% and 5.63%. So it basically appears that those who suffered a cardiac arrest in the day have a slightly higher chance of success or higher chance of survival than those who suffered at night. In this last example, we're going to again just do the hypothesis test and confidence interval for this following example. In a random sample of males, it was found that 23 write with their left hands and 217 do not. And looking at females, it was found that 68.5 write with their left hands and 455 do not. We want to use a 0.01 significance level to test the claim that the rate of left-handedness among males is less than among females. So we're going to be looking at 1, which is male, and 2 is going to represent females. Now we have to be a little bit careful because it does tell us x1 and x2. However, it does not actually tell us the sample sizes. Rather, what it tells us is it tells us the number of failures that we have, or in this case, the number of non-left-handed people. So x1 is in fact 23, but n1 is 23 plus 217. So we have a total of 240 males. Looking at females, we have 65 that write with the left hands, and we have 455 that do not. So n2 is going to be 65 plus 455, which is 520. So the null hypothesis, we assume that both proportions are the same. The alternative, which is our claim is that P1 is less than P2. Our significance level, of course, is just 0.05. And I went ahead and plugged all these numbers into our spreadsheet. And because this is less than P2, we get the Z test statistic as negative 1.17 and our p-value of 0.1213, or 0.1214 if you round it. In this case, our p-value is greater than 0.05. Because it is greater than our significance level, we failed to reject the null hypothesis. Looking at the critical value approach, we need to find the critical value where the area to the left is our significance level, which is 0.05. For the critical value, we want to find the z-score that has 0.05 to the left of it. And looking this up in the table, we end up with the critical value of negative 1.645. If we compare that with our test statistic is not inside the rejection region. So of course, we end up with the same conclusion where we fail to reject the null hypothesis in favor of the alternative. So we do not have sufficient evidence to support the claim that the rate of left-handedness among males is less than among females. For the confidence interval, because we use the same critical value as the hypothesis test version, this means that both tails will have 0.05 in them. This means that the middle area is 0.90. So we need a 90% confidence interval to find whether or not our proportions are the same or if they're different. Plugging these values in, and we find that our confidence interval is between negative 0.0685 and 0.0102. So it's roughly between negative 6.9% and 1%. So when we look at confidence interval, it has both a negative on one end and positive on another. This basically means that 0 is still inside the interval. And if 0 is inside the interval, that means that the difference of P1 minus P2 could in fact equal 0. This means that there is still a chance, or it could be likely, that there is no difference between these two proportions. So we're basically saying that there really isn't a difference in the proportion of left-handedness between males and females. So we are 90% confident the true difference in proportion of left-handedness between males and females is between negative 6.9% and positive 1%. Now, one thing I didn't really stress was making sure that you really need to have labeled what 1 is and what 2 is. And I want to just briefly illustrate that. Let's say that we do end up swapping these around. So let's say that we have 65 and 520 first. And then we have 23 and 240. This basically shows that we end up with similar percentages. In fact, this is negative 1% and positive 6.9%. But if we were to swap these around, we just have to change our wording in our conclusion. So this would be the case where we actually took the female percentages and subtracted those by those of male. So although we can still get the same conclusion, we just have to be really careful as to which one is our population 1 and which one's population 2, because messing that up can change our interpretation at the end. And that's the same for the hypothesis test. So notice, when I swap 1 and 2 around, that my test statistic will change from negative to positive, and my p-value will give me the complement. Now this is because I did not necessarily change this. If I switch this around, I'll get the same p-value as what I had before. The positive test statistic is okay. It's okay outside of my math lab. With my math lab's really picky about which one is the first proportion and which one's the second proportion. In general, unless it specifies it in the problem somewhere, typically the first proportion that it talks about or gives numbers for is P1, and the second population, or the sample that talks about, will represent 2. So, thanks for watching. I know this is a longer video. Sorry there's not a whole lot I can do about that, but um, let me know if you have any questions.